Okay, we'd like to thank everyone for coming and tuning in. This is the research results presentation for the study Improving Work Zone Safety Through Speed Management. This was a student study conducted at Ohio University under the direction of Dr. Deborah McAvoy. The student who conducted the work, Norman Summers, is here to give the presentation on the findings. If you are watching on the web and you have any questions, please email those to research@dot.state.oh.us, and we will forward those on to Norman for response. It's all yours, Norman.
All right. Good afternoon, guys. Again, my name is Norman Summers, and I'm here to present to you Improving Work Zone Safety Through Speed Management, a study I recently finished with the help of my faculty advisor, Dr. McAvoy. So with the constant need to repair and maintain and improve our roadways, there is an increasing number of construction zones popping up on roadways everywhere. These work zones create increased safety hazards not only to the workers themselves but also to the motorists that are traveling along these roadways. They introduce a constantly changing environment, from vehicles coming in and out to shifting lanes and things like that. And they also provide an influx of construction workers as well as vehicles that wouldn't normally be on the roadway. Many of the traffic crashes occur due to the driver performance and a lack of the risk assessment done on the driver's behalf in order to, speeds and things like that. And generally, in the past, so far, things have been done. The way that these things are fixed are by reducing the speed limits, which very few drivers actually adhere to. A study done by the National Highway Traffic Safety Administration in 2008 showed that about 31% of traffic crashes are due to excessive speeds on roadways, and the economic impact of this on society comes out to about $40.4 billion as of 2008. And also, the speed-related crashes killed about 12,000 people, about 300 of them being Ohioans. In these speed-related fatal crashes, 29% of them happened on dry roadways, a little higher, 35% on wet roadways, and the majority of the fatal crashes occurred on non-interstate roads. The people most likely to be involved in these crashes were males 15 to 24, and they were the most likely to be involved in these fatal crashes. Construction work zone crashes. Within these work zones, the most common type of crash is a rear-end collision. And the crash generally occurs within the work zone, the activity zone of the work zone itself. The typical cause for these are speed variance as well as congestion. So you have a lot of drivers who like to make a comfortable speed for themselves and travel along the work zone, and then you have the few drivers who are actually adhering to the speed limit themselves, creating this large variance within the work zone, and then when you throw a lot of vehicles on there, obviously this can cause a lot of problems. And in Ohio, between 2007 and 2009, there were approximately 3.5 crashes for every $100 million spent on work zone construction. So through past studies, it has been shown that these 4 police enforcement, flaggers, speed display units, and automated radar detection were the most effective at lowering speeds in work zones. The purpose of this study was to determine a low-cost and effective measure that was needed due to work zones continually popping up and becoming more and more prevalent on today's roadways, as well as restrictive budget and staff on law enforcement agencies across the country, and also an increase in speed-related crashes. So like I said, the objective of this study was to determine the safest and most effective countermeasure for the vehicular speed reduction within work zones themselves, and also to look at the driver performance and behavioral changes as a result of these specific countermeasures, whether they, cause someone to act erratic or, someone didn't know what it was or things like that. So there were 7 tasks laid out in front of me. One was to conduct a literature review. From there, I selected 20 different countermeasures, designed schematic drawings of each of the countermeasures in AutoCAD. I conducted lab experiments with the driver simulator that we have at Ohio University, statistically analyzed the data, completed the report, and then submitted it for final review. So the first step was to conduct the literature review. And from there, I used several web-based queries, one of the bigger ones being the TRB board presentation that they do every year, and finding different papers and things like that from there. I decided to date the papers no earlier than 2006 to continue to maintain proper ODOT standards and regulations and things like that, to not get too old, so that things haven't changed too much. So after selecting the 20 countermeasures, we decided that they can be put into one of three categories. Signs, physical signs on the roadway, the presence of vehicles, workers, or barriers, and then physical or geometric changes to the roadway themselves. So with the sign-related countermeasures, we came up with the variable speed limit, the highway work zone billboard, the dynamic message sign, sequential flashing lights, changeable message signs, monetary fines, emergency flash or traffic control devices, and speed photo enforcement. With the vehicle and worker present countermeasures, we have the presence of construction workers, presence of construction vehicles, presence of law enforcement, and then speed trailers as well. And with the final category, we had 3 and 4 sets of 3 rumble strips on the roadway, lane reduction from a 12-foot lane to a 10-foot lane, optical speed bars, concrete barriers, other channeling devices, changing them from barrels to tube cones, and then shifting lanes away from the work zone. So the next 3 slides show schematic drawings of what I came up with to present. So this is the first one, concrete barriers. So obviously you can see the channeling devices for the taper, and then along the entire length of the work zone there were concrete barriers instead, as well as the temporary traffic control signage previous to the work zone. The next one is the rumble strips. This is the 3 sets of 3 rumble strips. So as you can see, I have the length of how far they are to be placed. I used the previous study to show that these were the 3 most effective distances prior to the work zone in order to reduce speeds at the greatest amount. And then again, the rest of the work zone with all of the signs and everything else. And then this last one is shifting lanes. So actually shifting the 3 lanes, rather than closing a lane, just shifting all 3 lanes away from the roadway, or away from the work zone, instead of, like I said, closing a lane. So from there, after approval from ODOT, it was time to create the actual scenarios within the driving simulator. So to give you a little background about the driving simulator, we have, along with the driving simulator, the ability to create virtual worlds, and we can basically control anything we need in the virtual world itself, from the roadway type, whether it's a 4 or 5 lane highway to a dirt road, weather conditions, whether it's day or night, raining or snowing, and then specific roadway friction. If you wanted to create a snowstorm or something like that with minimal friction on the roadway, you could do that as well. And the vehicle itself is a complete front half of the vehicle with all of the regular vehicle amenities, acceleration and brake pedal, the standard dashboard instruments, the steering wheel, all of that good stuff. And then rear view and side view mirrors as well, which give you a look back at what was behind you, even though the screens themselves didn't actually show that. The vehicle itself also sits on a motion platform that provides inertial cues in order to shift the car. If you're accelerating, it pulls back a little bit, braking, it pulls forward, things like that. And like I said, the virtual world, the screens in front of there gave a 180-degree view of what you would see if you were in an actual vehicle. And then the rear view and side view mirrors allowed the driver to be completely engulfed in the 360-degree experience with things happening behind you as well. So with all of this, it allows each human subject to actively participate. And with this computerized data, it was collected at a rate of 60 hertz. So from there, the 20 countermeasures were divided into 5 scenarios with 4 countermeasures each. And we tried to divide the countermeasures up to take some from each category and spread them out, so you didn't have an entire scenario of just signs or an entire scenario of physical changes to the roadway. So from there, when creating the actual virtual worlds, I replicated everything replicated everything as laid out in Part 6 of the Temporary Traffic Control section of the Ohio Manual for Uniform Traffic Control Devices. So with all the signs and the spacing of the barrels and all that stuff. So we decided on a 3-lane straight roadway, flat, with the closure of 2 lanes that switched back and forth between closing the left 2 lanes and the right 2 lanes, so that it didn't allow the participant to shift over to the left lane and then just stay there for the entire length of the scenario. And each work zone was approximately a mile long with 1 countermeasure in each of those work zones. So like I said, they were divided up into 5 scenarios, each with polling from each category. So as you can see, we have a sign, and in each category we have the presence of workers in one, the presence of vehicles in another, the presence of law enforcement. And then there were some that we combined, so the speed trailer plus the law enforcement, to see if that was effective. So yes, this is the way we laid out the 5 scenarios. So each scenario took about 10 minutes to drive through, for a total of about an hour of driving. The reason we chose the 10 minutes and the 4 scenarios in each one was that in previous studies done with the simulator, we found that boredom and motion sickness tends to set in around 45 minutes of driving. So we tried to limit the amount of driving as much as possible within the scenario. And we also gave breaks in between each one, so if the driver needed to step out, take a breather, get a glass of water, something like that, they were allowed to do that, and they didn't need to sit through the hour-long session all in one sitting. And this also obviously ensured that there was minimal skew of the data. So with each countermeasure being developed in the virtual world, some of them were as simple as, like I said, just taking tube cones and placing them in place of the barrels. Other ones required more complex computer codes, such as taking the real-life speed of the driver in the simulator and displaying it back to them on the screen. That one was a little bit more difficult. Also, giving cues to the motion platform, an example for the rumble strips, causing the vehicle to shift up and down while the participant was driving over the rumble strips, was another one that was a little bit more difficult to control. So with all of those, they were all created. And so after that, the creation of the virtual world, we needed to gather our human participants. So we took a sampling of the driver population of Ohio, targeting specifically those males 15 to 24, because they were the most likely to be involved in these fatal speed-related crashes. And we also collected additional data from the participants along with the computerized data. We gave them a pre-test as well as a post-test questionnaire. So some of the pre-test data, you can see here we had about 56% males with the rest being females. The age range was about what we needed with the 15 to 24 years old. And then we also asked them several questions. How often do you encounter work zones? Do you speed during work zones? Have you ever received a ticket in a work zone? Things like that. So as you can see, 64% claimed that they had not sped through work zones, while most of those people had encountered work zones on an often basis. So then after taking this pre-test questionnaire, each participant was given a standard set of directions, the same directions for each participant, to ensure that there was no bias or anything like that. We also ran them through two different adaptation scenarios at the beginning. One of them was just driving on a straight roadway, and then the other one was shifting lanes back and forth. And this was to ensure that they had familiarity with the car and the controls and the simulator experience. And some of the people, get motion sickness right off the bat, and so that helps us, rather than running them through 2 or 3 of them and then them falling out of the study. This ensured that they knew what they were getting themselves into and were going to experience in the study. And they were also instructed to treat this simulator experience as if they were driving to and from work in their own vehicle on an everyday basis, to again create the most realistic experience we could for these participants. So while driving on the roadway, we collected speed, lateral placement of the vehicle within that own travel lane, as well as collisions if they happen to sideswipe a barrel or anything like that. So for the speed collection data, we looked at the speed before encountering the specific countermeasure, while encountering the specific countermeasure, and then after the countermeasure itself. So before the countermeasure, speed was taken approximately 500 meters before and after the roadwork 1 mile sign, or immediately following the roadwork 1 mile sign. And after countermeasures were taken following the end of the taper as they were transitioning back into the 3-lane roadway and normal travel. If the countermeasure was a single entity, like a sign or a vehicle or something like that, the speed was measured within a 500-meter radius of that specific countermeasure. If the countermeasure was concrete barriers or shifting lanes, and it spanned the entire length of the work zone, we took the speed throughout the entire length of the work zone as well. So for the lane placement data, we assessed this data allowed us to assess the ability of each of the participants' ability to stay within the center lane of their lane of travel at that time. So it recorded the data as a relationship to the center line of the roadway, which was measured as 0. And if they were traveling to the right, it gave a positive number, and to the left, it gave a negative number. So we can see where exactly they were within the travel lane itself. And this was measured through the entirety of the work zone. So this is the speed data. As you can see through each of, they're just listed in each of the scenarios. We have the mean, standard deviation, and then the minimum and maximum. And you can see the majority of them lowered speeds above 10 miles an hour. There were several of them that did not. The changeable message signs, the other channeling devices, the concrete barriers did not. But for the most part, they were all generally effective in lowering speeds to a certain extent. With the lane placement data, as you can see, this the reason some of them are positive and negative, and you can see it goes back and forth, is because, like I said, the left lane was closed, the left 2 lanes were closed, and then the right 2 lanes were closed. So it did bounce back and forth. So from there, we needed to statistically analyze all of this data that we had. So with our sample size being known, as well as an alpha and beta level being selected, we used this equation to determine a detectable difference in the means. So we knew that we needed a 95% confidence level, or alpha being 0.05, power of 80%, or beta being 0.2, and we had 25 participants. So from this, we came out with a detectable difference in mean of about 2.33 miles an hour for the speed, and a detectable difference of about 0.44 feet for the lateral lane placement. And past studies have shown that a difference in means of speeds ranging from 1 to 5 miles an hour were acceptable. So due to this previous research, we came to the conclusion that this 2.33 miles an hour that we came up with for a detectable difference was acceptable. So from there, we took the we needed to determine the differences between each of the countermeasures to see which one was the most effective. So we used the ANOVA test, the one-way ANOVA test, to do this. This test allows us to get the difference between several means all at one time. A student's t-test could have also been used, but that only allows you to statistically analyze two different means, and many iterations of this would have been needed to go through each of the 20 countermeasures. And also a downside with the student's t-test was that the type 1 error, or the incorrect rejection of the null hypothesis, was very large, or tended to be large when that type of study was done. So at the end of the day, we came up with a one-way analysis, or the ANOVA test. So the ANOVA test only reports whether or not a difference exists within the data, and it doesn't specifically point out whether or not one is more effective or there's more difference between one or another. Like I said, it only just tells whether there is a difference or not. So we needed several post hocs in order to decisively determine which of the countermeasures stood out and was the most effective. So the Tukey Posthoc test was used for the speed analysis data due to the homogeneous variances and equal sample size. And the Games-Howell Posthoc test was used for lateral lane placement due to the heterogeneous variances. We also determined the effect size for the data to consider whether it was practically significant or statistically significant. The effect size is calculated, is basically a measure of the number of standard deviations the difference is away from the null hypothesis. And the effect size comes in, there's three categories. If it is above if it's lower than a 0.2, it's considered a small effect. If it's 0.5, it's a medium effect, and if it's 0.8, it's a large effect. So from those three criteria, we calculated the effect size. So for the speed data results, the null hypothesis was obviously that there's no difference between mean speed deviations for the 20 countermeasures. So based on the results of the ANOVA test, the null hypothesis was rejected for the speed data. So as you could see, we had each countermeasure was effective to some degree at lowering the speeds, but we needed to figure out which one. The effect size was 0.37, which indicated a medium effect, meaning that the speeds were statistically and practically significant in lowering the speeds, or the differences were practically and statistically significant. Since all of the mean speed deviations were positive, the speeds were higher coming into the work zone and lower during the countermeasure, which meant that, again, all of the speed reduction countermeasures were effective to some degree. The results of the Posthoc test indicated, they were lengthy, so unfortunately they're not listed here, but they did show that the presence of construction workers, the presence of construction vehicles, presence of law enforcement, and speed photo enforcement, as well as shifting lanes, were the most effective at reducing speeds, and those can be shown by the speed data itself. The least effective countermeasure were the three sets of 3 rumble strips, the concrete barriers, other channelizing devices, and changeable message signs. Those 4 were the least effective at lowering speeds. Again, under 10 miles an hour was the mean speed reduction for those 4. The results that we came up with also tie back with previous studies that have been done that show that the presence of workers, construction vehicles, and law enforcement are the most effective at reducing the average speed. So this is the list, as well as the mean speed and the rank at which they lowered the speed. And you can see the top 4, the presence of workers, construction vehicles, as well as law enforcement and speed photo enforcement, are the top 4. And then the 4 at the bottom, the changeable message signs, other channelizing devices, concrete barriers, and the 3 sets of 3 rumble strips. The lane placement data, the null hypothesis for there obviously was that there was no difference between the mean lane placement and the countermeasure before and after the countermeasure was put in place. And based on the analysis, again, with the ANOVA test, it was found that the null hypothesis was rejected. The effect size for this was calculated to be 0.88, indicating a large effect, meaning that the mean placements were statistically and practically significant. A positive value, again, indicates that the participant is traveling right of center, and a negative value indicates that they are traveling left of center. If these values were too high on either end, either positively or negatively, it could indicate that there was either an intrusion into the work zone, or it could indicate that they had the potential to sideswipe other vehicles on the roadway or run off the roadway. So it was desirable to come up with a countermeasure that reduced speeds as well as allowed the driver to maintain their center of line travel and not have them go too far either way. So the simulator lanes were 12 feet wide, and assuming a 7-foot vehicle width gave us about a 2.5 clearance on either side of the vehicle. And it was assumed that a clearance of less than a foot would be unacceptable in terms of safety and would cause risk to, again, the motorists as well as the workers themselves. So the Games-Howell Posthoc Test, which was used for the lane placement data, indicated that the countermeasures would be divided up into 6 different categories. Vehicles located 1.1 feet from the lane line nearest to the work zone, 1.5 feet from the lane line nearest to the work zone, 1.5 feet from the lane line nearest to adjacent traffic, 0.82 feet from the lane line nearest to adjacent traffic, on the lane line for adjacent traffic, and a foot intrusion into the adjacent lane traffic. So based on this less than 1 foot rule, clearance rule, the countermeasures that fell into categories 4 through 6 were considered to increase the risk to both the workers as well as the motorists themselves. So here's the results for the lane placement data, and you can see on the left column the categories that each one fell into. So anything in 4 through 6 obviously is unacceptable and would not be suggested to be used, with lane reduction being the most ineffective, causing vehicles to shift very far to the outside of the roadway to avoid hitting the obvious barrels and tube cones and things like that. So following this, after the participants drove through each of the 5 scenarios, they were given a post-test questionnaire, and it was just one simple question, and it was, which 2 countermeasures do you feel were the most effective, in your opinion, at lowering your speeds? The presence of construction workers, as well as the presence of law enforcement, were the ones to be found most effective in their own opinions. Speed photo enforcement, again, also, which proved effective in the simulator data, was also in one of the top 3 for the post-test questionnaire. And here are those values. Again, with the top 3, law enforcement, construction workers, and speed photo enforcement being the most effective. One thing that I personally found interesting was optical speed bars. It was a paper I came across, and it was several people had approached me after the scenario and said that they weren't exactly sure what it was, and so they kind of slowed down. But again, it's top 4 or number 4 for the responses of lowering speeds. So in conclusion, again, the objective of this study was to determine the most effective countermeasure for speed reduction, the most effective countermeasure of speed reduction in work zones, and the simulator experiment research methodology was designed to allow active participation of the subjects without putting them in real-world harm, obviously. Several of the countermeasures that were chosen have been tested, obviously previously, which is how I came about these 20 countermeasures. But this specific study allowed us to test all 20 of them in one common roadway, so all 3-lane flat roadway. And it gave us kind of a sense of all of them together, which one was the most effective. So following this, the advantages and the disadvantages were outlined for each countermeasure. With the top three, the presence of workers, it's obviously the most effective, and it keeps drivers further away from the work zone. But again, it increases the potential for side swipes because vehicles seem to tend to try and be as far away from the workers as possible, so they could intrude into other lanes. And it does not decrease the speed when workers were present. One of the things we did in the simulator setup was the construction zone was a mile long, and I put construction workers in the first half mile and then not in the last half mile. It was shown that the drivers tended to speed up once the construction workers were not present and started to get back up to normal speed when there wasn't any activity going on. Again, with the presence of construction vehicles, it's a very good effective measure. It keeps, again, workers or drivers away from the work zone, but it does, again, impact the driver lane placement, increases the potential for sideswipe crashes, as well as does not decrease speeds when the workers are not present. And then law enforcement, costly to the jurisdiction. You actually have to have vehicles present, but again, it is very effective and does not impact the driver's lane placement. With the bottom three, the emergency flasher control devices, it keeps drivers away from the work zone, but it impacts the driver's lane placement and again may increase the potential for side swipes. And then with lane reduction being the least, it provides additional space for construction, which is an advantage, but at the same time tends to push vehicles as far away from the construction zone as possible. So following all of this, we concluded that further research should be done in the field to validate some of the specific countermeasures we found. Speed photo enforcement. Several studies done in Maryland have shown that speed photo enforcement has great promise and could generate additional revenue for the specific transportation agency that it's being used for. And additional research should be conducted on certain measures as sequential flashing lights or the emergency flasher control, traffic control devices, or optical speed bars, things like that, to gain more knowledge on their effectiveness without any additional risks to either motorists or workers. Questions? Yes?
For the scenarios where, For the scenarios where a speed reduction was implemented, was it always 65 to 55?
Correct.
And then another question, I'm just curious, how many participants did you actually have to turn away for illness or motion sickness? Any at all?
There were 3 or 4 that there was 2 or 3 that said right off the bat through the adaptation scenarios that they didn't think they would be able to handle it, and then there were 2 or 3 that made it through 1 or 2 of the scenarios and got motion sickness. And I think what it is it's the tendency when you're in a vehicle, you actually get the motion of if you turn or shift lanes and things like that. And in the simulator, it's obviously all happening in front of you, but you're not feeling any of it. So some people just couldn't handle it. So yeah, I'd say probably about 3 or 4 people we had.
Out of many total?
We had 25 participants.
And then when they were running through each of the individual groups of scenarios, so the 5 different groups and then 4 groups and 5 in each one, did it vary up? Like you said, sometimes the left lanes were closed, sometimes were right, so they would go through and then, the right lanes were closed in the first scenario and then the left lanes closed, or was it all like right lane closures within one scenario and left? Or or work positions, rather?
Yeah, it bounced back and forth. In each scenario, we closed the left lane or the right 2 lanes first, and then the left 2 lanes and right 2 lanes, and it just went back and forth again to not allow the participants to travel, shift over to the left lane and then just stay there for the entirety of the work zone. And another thing we did was we also, to decrease bias, switched up each scenario. So we labeled them A through E, and participant 1 got scenario A first, but participant 2 got scenario D first, and things like that. Because I noticed as I ran more and more participants that, again, with simulator boredom and things like that, that by the 4th or 5th scenario, they tended to try to just kind of speed through it to just get done and not have to sit in the vehicle anymore. And so that's another reason why we switched them up, so that there wasn't, scenario E wasn't, there was no decrease in speed at all. So.
What was the age group of these participants?
The age group, we used several classes. I went into several classrooms down at Ohio University, so it's generally college-age kids, 18 to 22, 23, and then there were several graduate students as well that participated. But it was all on a voluntary basis. I asked my friends down at school. I asked coworkers if they wanted to participate, and so yeah, generally college-age kids.
What an optical bar is, speed bar?
Yeah, an optical speed bar. It was actually something I'd never heard of, and I came across it in a study. But it's basically placing horizontal lines along the roadway that are spaced at a certain. They start out at, I think they said 21 feet apart, and then as you're they get closer and closer, so that as you're driving at a constant speed, you get the illusion that you're speeding up because the bars are passing you by quicker and quicker. But one of the, to go back, one of the downsides to the optical speed bars was that it creates potentially confusing pavement markings, along with, all of the shifting lanes and everything else that are already on the roadway with construction zones.
I'm not familiar with the term highway work zone billboard. Can you describe what that is?
Yeah, highway work zone billboard. I came across a paper that actually Dr. McAvoy had completed, and it's basically testing the difference of, it's like the slow down, my dad's a worker, like the things that kind of take real life things like children and, like that kind of thing, and puts them onto signs to kind of connect with what's going on here and almost humanize to a certain extent that the workers are, people, and you're impacting their safety and all that other kind of stuff. So. Mm-hmm.
Okay, you have a question from the web. In Montana, we have a large number of crashes in the back of queues with drivers not paying attention. Have you performed any work with flagging stations with your simulator?
We did not do any flaggers or anything like that. We, on the roadway, in order to ensure that the countermeasures were what was being studied, we decided to we decided to have the simulator vehicle be the only vehicle on the roadway, and so there wasn't no ambient traffic. They were the only ones, so their speed was not affected by the ambient traffic breaking in front of them or people passing them by or cutting them off. So we did not do any research with flaggers, but yeah.
Yeah, we have done none to date with flaggers.
Okay, with no more questions, we'll go ahead and end the webinar for today. If you come up with additional questions that you would like to have answered, you can email those to research@dot.ohio.edu. www.state.oh.us, and we will forward those on to Norman and Dr. McAvoy for a response. This presentation was recorded. It will be available on the research website in a couple of weeks that you can share the link with your colleagues who are not able to attend, as well as a PDF version of the actual PowerPoint slides. The final report will also be available on our website in a couple of weeks. If you're interested, you can feel free to download it and read the entire report. Thank you very much for participating.